One of our main subjects of study is functions. We're going to be studying functions and we want to get to know things about functions, attributes, characteristics about functions. Among those, we have um, the change of rate or how much the function increases or decreases. Um, and among that, we have what is called the difference quotient. So the difference quotient measures how much a function increases or decreases. And that's why we study the difference quotient, because it tells us an attribute, a characteristic of functions. There are two main formulas, and these are not, I'm showing two of them here, but these are not the two that I'm talking about. This is the same, yeah, this is one formula. This is one formula. I mean, writing it in two different ways, but here I say that there are two formulas, but those are not the two that I'm speaking about. These are just the same. Yeah, they're the same. Yeah, that could be confusing because here I'm talking about two formulas, but those are not the two. This one is one, so that is one. And then there's another formula that I'm not going to show you right now or in this video. And in books, you will see this as the formula, which makes sense because this is the simplified version of that. Oftentimes, I prefer to write this, which is not the simplified version. So technically speaking, we should write this one instead. But the reason why I'm showing this is because this tells us more of what's going on. We have y2 minus y1 over x2 minus x1. So this is really rise over run. This is the slope that's going on. If we simplify the denominator, then it's not so clear that we have x2 minus x1. If you have x plus h to then subtract x, of course we can do x minus x, which is going to give us 0, and h plus 0 is just h. But here, it's not so clear that we are doing x2 minus x1, so it isn't as clear that we have a slope. Now, again, this is the formula books, and we should use. This formula comes from this, which tells us that we are doing y2 minus y1 over x2 minus x1. And we have to be quite good at coming up with the difference quotient of different functions. So in this video, we're going to show examples of how we find the difference the difference quotient of different functions. All right, so let's start with example 1. Okay, so in all of those examples, we're going to find the difference quotient of the given functions. Let me write that down here. Yep. In the following examples, we will find the difference quotient of the given functions. Okay. So let's start with f of x being equal to 3x squared minus 5x plus 7. Okay. Now, we're going to find the difference quotient, which is this. The simplified version is this one. This is the one we use. Yep. And forgive me to repeat myself, but it came from y2 minus y1 over x2 minus x1, which is the formula for the slope. So this is really a slope, a rise over a run. What happens is that the run doesn't look like a run, it's just a plain h. The formula calls for finding out what f of x plus h is. We're going to plug this into the formula. So perhaps we should do this You see, there's two modalities. Some people will plug it into the formula all at once, and some people will not. Let's just plug the whole thing all at once, and then simplify. So when we plug this function into this difference quotient, we're going to get something that is going to get complicated quickly, but then things are going to simplify also. So let's do that. Okay, so f of x plus h minus f of x over h is initially, I don't know if it's going to fit in here. I'm going to put it underneath just to be sure. So this continues here. Now, there's no need to put an arrow. I'm going to put an arrow, a dotted arrow, but there's no need to put the arrow because whenever we have an equal on the next line, that means that we're just continuing the line. And I'm writing it, the next step, underneath because I don't know if I'm going to have enough space here to do what I'm going to do. Okay, so we're going to have a big fraction. On the numerator, we're going to have x plus h quantity squared, because remember what f does. F tells us to square the input, multiply by 3. So we're squaring, multiplying by 3. Take away 5 times the input, add 7. Okay, that's just this part. Then we have to subtract f of x. I'm going to put this, I'm just going to leave it alone, minus f of x, but f of x is that itself. 3x squared minus 5x plus 7, close the parenthesis, all of that over a single little h. Yeah, this fraction is top heavy. There's a lot of stuff here, and it's going to get even worse because we're going to expand that. Now, one thing we can notice right away is that we're going to add 7, and then we're going to subtract that other 7. So we can start simplifying this a little bit. Again, we're adding 7, and then we're going to subtract 7. I'm going to put a hat instead of crossing it off so that we can tell what we did. If you start crossing things off, sometimes it is hard to read what we crossed. So here, I'm putting a little hat on top of those, indicating that we're going to simplify them, but we still can read what was going on. So we're adding 7 to then subtract that 7, and that those two 7s go away. While that is happening, we are going to FOIL this out. 3 times, now remember, this is x plus h times x plus h. I'm going to let you figure this out. If you want to pause the video so that you can convince yourself of what we're going to get after doing x plus h times x plus h, go ahead. So we're going to end up with x squared plus 2xh plus h squared. And remember, that comes from x plus h times x plus h. So the first terms multiply the outer terms, the inner terms multiply, the last terms multiply also, and then we consolidate, and we end up with this. So we're squaring this quantity. Minus, so we're going to distribute this over the x plus h, 5x minus 5h. All right, the 7 is gone. We distribute this negative over the other two that are left, minus 3x squared. And then we have a double negative situation going on here, so that is plus 5x. All of that over h. Okay. We notice that we are subtracting 5h, rather subtracting 5x to then add 5x. Negative 5x and 5x add up to 0, and 0 does not affect the sum on the numerator. So we're going to put a hat on top of those. Those two terms will simplify. Negative 5x and positive 5x added together is 0, and the 0 does not affect the sum. Okay. While that is happening, we're going to distribute the 3 into this polynomial. So we have 3x squared plus 6xh plus 3h squared. Those two are gone, minus 5h minus 3x squared. All of that over h. All right. The only thing I notice we can simplify is the 3x squared with the 3x squared. So those two are going to simplify down to 0, and 0 added to what is left is still what is left. So we have now 6xh plus 3h squared minus 5h, which now we simplified with the h in the denominator. Now, it would be wrong to simplify this h with that h, and that's it. No, because this is not a factor of the entire numerator. We have to have a factor. So that cannot simplify just with one of the h's. Yeah. Yeah, and that creates another problem. What if I want to simplify with this h? Then the answer is different, and we cannot have different answers. So what we do is factor out an h, and it doesn't matter where you put the h, in the front or on the back of what we're factoring. Let's put it in the front, h. So we're going to factor h out of this, and that is 6x, plus 1h out of that is 3h, minus the h out of the 5h is just the 5 over h. Okay, now we may simplify this h with this h because the h is multiplying this polynomial, but then we're going to divide by h, so they undo each other. Multiplying with h to then divide by h, they undo each other. So might just as well not do the multiplication and the division. So what we are left is with 6x minus 3h, rather plus 3h minus 5. So this is the final answer. All right. That is the slope of this parabola. It turns out that this is a parabola of 2 points. One point that is generated by plugging a number into x, and another point is generated by plugging a number into h. It gets a little bit lengthy to show on the graph, unless I'm a little bit vague, but I'd rather go in a different direction. So when we ask for the difference quotient, this is it. Stop here. That's the end. Okay. That's why I boxed it. But I want to tell you something else. We are one step short from calculus. In calculus, we find the derivative. And I'm not going to ask you anything about calculus because this is an algebra class. But we are one short step from finding the derivative. If you set h to be 0 in this situation, what is left, which is 6x minus 5, is the actual derivative, as in calculus, of this function. The derivative of this function is 6x minus 5. If we neglect the h, then what is left over is exactly the derivative of this function. So there's value on doing this. Okay. At this point of the game, we want to make sure we know how to find the derivative of a quadratic function. So this is a quadratic function, and we have to know how to handle it. There are a couple other functions we have to know how to handle. So let me show you example 2. Yeah, this example is completely different than example 1. Example 2 has to do with the square root. So I'm going to use the same name, f, but we're going to have a different function. Let's start with something very, very simple. The square root of x. It isn't too simple, but it is the simplest one we can come up with, the square root. So this is the problem. And we want to figure out the difference quotient. So the difference quotient is f of x plus h minus f of x, all of that over h. Okay, and the reason is because this formula, which is the one we're using and we're going to continue to use, comes from y2 minus y1 over x2 minus x1. What happens is when we simplify that, we end up with just the h. All right, in this case, we have the square root of, okay, so the function calls for the square root of the input, whatever the input is. Right now, the input in this left side of the numerator is x plus h. So all of x plus h is going to be in the root, minus square root of x over a h. Technically speaking, that's it. However, for purposes of working with calculus, in calculus, what we're going to do is set the h equal to 0. And consequently, we don't really want to leave an h in the denominator because we may never, ever, ever divide by 0. Never, ever, ever, ever divide by 0. So if we left the h here, then we would be doing that, dividing by 0, because eventually, not right now, but eventually in calculus, we want to send this guy to 0. And so this creates a problem. So we want to simplify. And the way we simplify this particular problem is different than the way we simplify this problem. And that's why we have different examples, because they are simplified differently. In this example, we expand, start adding and subtracting things that are equal to 0, and then factor the h, and then after that, we simplify to something that has no h in the denominator. Here we cannot do that because there's nothing to expand, so that doesn't work too well. What we're going to do is multiply by what is called the conjugate of the numerator. We're going to multiply by the quantity square root of x plus h minus square root of x, but we have to divide by the same quantity. Otherwise, we're going to be changing the value of the fraction, x plus h minus square root of x. So that is the trick in this kind of a problem. If we have a root, start out by writing out what the difference quotient is, and then multiply by the conjugate on the numerator and denominator. This is actually the number 1. So we are not really changing the value of this fraction. Oh, I made a mistake. I'm going to be able to fix it very quickly. If this is not the conjugate, this is the same thing. We need to put plus instead. There we go. So this minus that times this plus that. All right. So let's continue here. We're going to FOIL this out. So this times this root times this root, well, it's just going to be x plus h. This times the outside, so the first times the outer of the second binomial will be, let's see, plus square root of x plus h times the square root of x. And then the inner terms will be minus square root of x times the square root of x plus h. And then the last terms, well, the root of x times the root of x is x. But then we have negative times positive, so we have minus x. In the denominator, let's not distribute, because our hope is that this h will go away. And the only way it can go away as part of the denominator is if we have a factor of h in the numerator. So don't distribute this on here. What we're going to do is simply write h and square root of x plus h plus square root of x. Now we're going to simplify the numerator. Observe that this product is exactly the same as that product. If we use the commutative property, we can turn those around and have square root of x plus h first and square root of x second, just like this one. This is plus and this is minus, which means they're going to go away. They're going to add up to 0. We're going to be adding this quantity, but then we're going to subtract the same quantity. So that's like doing nothing. So those two are going to neutralize each other. I'm going to take one more step. Yep. Well, actually, we could do that here too. X minus x is 0. X minus x is 0. So that's also going to go away. So those two go away, and so do the x's on the numerator. So the only thing that survives in the numerator is an h. The denominator is the same, square root of x plus h plus square root of x. And now the h's do simplify because we're multiplying h times this quantity. So we are dividing by this quantity, but in the division, there is a multiplication. So I might just as well simplify those two. So this is 1 over square root of x plus h plus the square root of x. All right. Now, the value of doing this is that if we set h to be 0, then we are not necessarily dividing by 0. We are okay. This is our final answer. This is the simplified difference quotient of this function. Yeah. Yeah. Okay. Let's do a third example. Let's see if I can squeeze it in here on this page. Example 3. F of x equals 1 over x. So there's our function, and we want to find its difference quotient. So we're going to do f of x plus h minus f of x, all of that over h. All right. So this function says whatever the input is, do 1 over that input. Again, whatever the input is, 1 over the input. So we're going to do, okay, so we have a big fraction, 1 over the input. The input is x plus h. And then we're going to take away the function itself, which is 1 over x. Now we have to simplify this, especially because we don't want to have h in a denominator like so, because eventually in calculus, we would want to send h to 0, and we cannot divide by 0. So we have to do some algebra to simplify this h. This h has to go away in this kind of a problem. There's a couple ways to go about this. You can multiply the numerator and denominator by the common least common denominator of the two fractions, or we can simply combine the fractions first. So let's do that. Yeah, this is going to take a little more space than what I anticipated, but that's the way it goes. So 1 over x plus h, that fraction, we're going to multiply it with x over x. So now we have the same denominator for this fraction, minus 1 over x, which is going to be multiplied with x plus h over x plus h. All of that over h. Yeah. So this equal should line up with the line of the fraction. It shouldn't be floating up that high. There we go. Because this is the fraction. A numerator, which is rather complicated, has more fractions, but this is the main fraction. This line corresponds to the main fraction of this expression. All right. So now we have the same denominator, x and x plus h, x times x plus h for both of the fractions. Let me write that down. So we have x over x times x plus h minus x plus h over x times x plus h, all of that over h. Now let's combine the two. Now there is something important that is going on in the combining of those two. Yeah, so let's keep the h down here, and we're going to have a fraction with denominator x times x plus h, and in its numerator we're going to have x minus the quantity x plus h. That is very, very important. And I'm putting a bracket to emphasize that this is still the numerator and this is the denominator of this big fraction. Again, my equal sign doesn't line up too well. You may be thinking, well, so what? Yeah, uh, math requires us to be very, very mindful of all of those little details. All right, so something to notice here is that we are subtracting the entire pair, not just the x, but the entire pair, because this subtraction was about subtracting the entire fraction. So when we distribute this negative, yes, we're doing x minus x, and that's going to be 0, but also the negative is going to be affecting the h. So we're going to have negative h, which is a big deal. So we have negative h over x times x plus h over h. Okay, let me copy this on the next page. So we are continuing example 3. We have negative h. I'm just copying this down. X times x plus h in a bracket over h. Okay, and again, there's a couple different ways to go about this. We can multiply by the reciprocal of, because we need to simplify the fraction. So when we multiply by the reciprocal, we're going to end up with negative h over x times x plus h times the reciprocal of this h, which would be 1 over h. Now the two of them simplify down because we are multiplying by h to then divide by h, so they undo each other. And we finally end up with negative 1 over, the negative remains there, only the h is simplified, x times x plus h. So this is the difference quotient. One thing I want to keep emphasizing is, even though we're doing one kind of difference quotient, this is the formula. We do different things depending on the kind of function we have. So for this quadratic function, we do this work. If you have a root function, we do something different. We multiply by the reciprocal. If we have a fraction like this one, then we simplify fractions. Those are 3 different ways of doing difference quotients depending on the function we have. Yes, the initial formula is the same, but the way we simplify after we plug in the function is different. We cannot apply the same thing over and over again. Over the years, I have noticed that students apply this method of multiplying by the conjugate to everything. Or maybe, yeah, that's the most common mistake I've seen. They say, oh, we're going to multiply by the conjugate, and that's going to do it. Well, that only works if we have a square root. Otherwise, in this case, we did not multiply by any conjugate. We just expanded the polynomials and simplified as we went along. Versus this one, there was no expansion of polynomials here. There was no multiplication of conjugate. What we did was simplify the fractions. All right, so we got to be careful with the different kind of examples we have at hand. That was example 3. We're going to move on to example 4. Example 4 is actually easier. The last couple of examples we're going to do well, at least for now, are going to be simpler. So simple that it is almost confusing. I think when something is way too simple, it can actually be more confusing than something that is not so simple. So let's start out with this function. Let's say it is 9x minus 10. All right, and we want to find the difference quotient of this, the rise over the run. Okay, so applying the formula, f of x plus h minus f of x over h. All right, so we're gonna, now remember what the formula calls for. Whatever the input is, multiply by 9 that input, and then subtract 10. So when we are using this formula, the input is x plus h. So we're gonna multiply x plus h, the entire input, by 9. 9 times the quantity x plus h minus 10. And then we're going to subtract 9x minus 10. All of that over h. Okay, so initially that's what we have. All right. Let's do a little bit of algebra. Let's distribute the 9 over those two. So we have 9x plus 9h minus 10. Distribute this negative over those two, minus 9x, double negative, plus 10. Okay, so 9x minus 9x are going to simplify down to 0, negative 10, and positive 10 are going to simplify down to 0. So we end up with 9h, 9 times h over h. The two h's simplify, and we end up with 9. That's it. That's the difference quotient, which should not surprise us. You know very well this is a straight line. What is the slope of this straight line? What is its slope? Well, it's 9. And what we are finding is a slope. Well, the slope has to be 9 because that is the slope of the line. It wouldn't make sense that the slope is something else other than 9. It has to be 9. So now, when we ask to find the difference quotient, we expect students to show all of this work, because even though they probably will know in advance the answer is going to be 9, they still have to do this work to show how the formula works. But yes, every time you have a straight line, the slope, a straight line such as mx plus b, the slope will always be the slope, which in this case is 9. Okay. Example 5. This is the easiest example, and yet it is the most confusing one, in my opinion. F of x equals 8. In a previous video, we had this example. F of x equals 8. This is the constant function. This is the constant function. How can we tell there's no input in this formula? That means that the output is 8 regardless of the input. The input has nothing to do with the output. The output will always be 8. What is f of 5? 8. F of 7? 8. F of 1,000? 8. F of negative 1 million? 8. No matter what, the output will be 8. Okay, so let's find the difference quotient. Same formula, f of x plus h minus f of x. All of that over h. Okay. By the way, we're assuming, even though h will eventually be 0, while we are figuring out the difference quotient, we're assuming h is not 0. That's a little confusing because time has something to do with this. So now that we are finding the difference quotient, h is not 0. Later, when we find the derivative in calculus, then we're going to send h to 0. Notice that I didn't say that h will be 0. We're going to send h to 0, which is not quite the same. But anyway, that has to do with limits. So anyway, let's go about this. So what is f of x plus h? What is f of x plus h? Think about that. What is f of x plus h? Well, this is the constant function. So no matter what the input is, the output is 8 minus f of x. All right. So f of x is also 8. Yeah, remember the constant function says regardless of what the input is, the output is 8 for this case. And of course, 8 minus 8 is 0. While we're finding the difference quotient, we're assuming that h is not 0. So 0 divided by any number that is not 0 is going to give us 0. So in this case, and I should probably have mentioned that earlier here. In fact, I'm gonna come back to this and state that. So there's a note we're gonna add to this note when finding difference quotient. We assume h is not 0. We have to. Otherwise, it wouldn't make sense. Well, it would, but it wouldn't make sense to arrive to this conclusion. So there's an implicit assumption here. And let me emphasize that here. We assume h is not 0. Yeah. Yeah. In practice, we are changing the domain of this expression. In this expression, h could be 0. In this expression, it is not. So this equal requires this additional comment. As a matter of fact, that applies to all of the ones. Remember here, we simplify this h. The same assumption was taken. We assume h is not 0. That happens every time. When we simplify those two, yep, in this case, again, we assume h is not 0. Here, when we simplify those two, because we cannot divide by 0, but that is sort of implicit, but it is good to emphasize it. So the reason why those two are equal is because we're assuming h is not equal to 0. Assume h is not 0. And finally here too, in this example we did, when we simplify those two, we assume h is not 0. So that's why we have to make this note. When finding difference quotient, we assume h is not 0. Yeah. Let me add, so let me come back to this kind of example. This example is almost too simple. Let me add one other example that is a little more complicated than this one. Yeah, so we're going to label that example 6. 6. So we finished all the simpler examples: a quadratic, a root, simple root function, a fraction, which is a rational function, a linear function, and a constant function. So that's why we have 5 examples. This is the constant. The example 4 was the linear. Example 3 was the rational function. Example 2 was the root function. Example 1 was the quadratic function. But now I want to go back to another root function. So let's label this as another root function. Okay, so f of x equals 3x minus 4. That's not as simple. But the process of root functions are square roots. By root functions, we mean square roots. The process is very much the same. So let's figure this out. Okay, so the difference quotient will be f of x plus h minus f of x over h. This is going to take more than this page, and that's okay. So square root of 3 times the quantity x plus h, close the parenthesis. Then we still have to subtract 4 inside the root. So 3 times whatever the input is, take away 4, square root of all of that. Then we're going to subtract the function itself, 3x minus 4. And then we're going to divide by h. Okay. Let's distribute the 3x, the 3 rather, into the x and the h. So we're going to have square root 3x plus 3h minus 4 minus the square root of 3x minus 4. All of that over h. And now we're going to multiply by the conjugate of this on the numerator and denominator. So we will have square root of 3x plus 3h minus 4 plus, still under the root, square root of 3x minus 4. And then the same thing here, 3x plus 3h minus 4 plus square root of 3x minus 4. This is going to get ugly before it gets better. I'm going to continue on the next page. Okay, so this is going to be equal to one big fraction. Okay, so let me show you the shorter version of this, because I want to skip one step. We have a quantity a, pretend this is a minus b, and this is a plus b. Whenever we fold this out, we're going to end up with a squared, outer terms plus ab, inner terms minus ba, and then we're going to add, actually subtract b squared. Yep. So those two invariably are going to simplify, in the sense that this is the positive and this is the negative of the same quantity, AB, plus and minus. So those two are going to add up to 0. So we're going to end up with a squared minus b squared. That is the difference of squares. What happens is that this is the gigantic A, and this is A, and this is B, and this is B, and we have minus and plus, minus and plus. So the same situation will happen. We're going to have those two multiplied together, plus those two, minus those two. Now, those two minus those two together are going to add up to 0. That is like AB minus BA. So plus and minus of the same add up to 0. So those two are going to cancel, and we end up just with this minus those two. So those two minus those two, that is a special case of a special kind of multiplication. When we multiply conjugates, that's what's going on. I'm putting this in parentheses because this is not really part of that. I'm just showing you what's going on. So multiply this with that, and we're going to, the root with itself is going to give us 3x plus 3h minus 4. And then we're going to subtract this plus that. So we're going to subtract 3x minus 4. And that's it. The other two terms, multiplying this big A with this B would have been a huge two roots together. And then those two would have been another two roots together, one positive, one negative, and they simplify each other out. In the denominator, do not distribute. Keep the h there, and we're going to keep this other denominator with it. Square root of 3x plus 3h minus 4 plus square root 3x minus 4, close the bracket. Okay, the next step has to be done carefully, depending on how confident you are in your ability to do this mentally, or whether we want to distribute. I always prefer to distribute. It's, in math, measuring twice and cutting once is the best thing to do. Sometimes we go very, very fast, but then if we don't obtain the correct result, we have to go back and fix the mistake, and that actually may take more time than if we just went slowly and carefully the first time around. So the force simplify, 3x minus 3x. See, what I did is distribute the negative carefully, because yes, we end up with negative 3 and the x, but then we end up with positive 4. That's very easy to miss. So we have just 3h over h times the quantity square root of 3x plus 3h minus 4 plus square root of 3x minus 4, close the bracket. The 2h is simplified because we're multiplying by h to then divide by h. We're assuming h is not equal to 0. So we have 3 over, there's no need to put a bracket anymore because this h is gone. Square root of 3x plus 3h minus 4 plus square root of 3x minus 4. And voila, there is the difference quotient. So problems can get difficult, lengthy, very quickly, very, very quickly. Yeah, let me write down here that we assume h is not equal to 0, and that allows us to simplify, because if h was 0, then we wouldn't be able to simplify. We wouldn't be able to divide by h at all. All right, we're going to stop the video in this example.